The purpose of this video is to familiarize the users with some of the more advanced tools and features used in controlling the 3D rendering. This video was recorded using CubeVue version 2809. Some of these features are available in earlier versions of CubeVue as well. Starting off with a quick review of the view direction controls. AP is your default direction, as when the patient is initially scanned. LL stands for left lateral. PA stands for posterior anterior. RL stands for right lateral. We have a view up from the bottom, a view down from the top. We also have, starting back in our original position, rotation on the x-axis plus 90 degrees, meaning in this case 90 degrees of the toes coming up. X minus 90 gives you the opposite rotation. Rotating in the y direction, we are moving plus 90 degrees or minus 90 degrees. And in the z rotation direction, z plus or z minus as well. There are also two special view directions for the 3D rendering. When we go to C, anterior posterior, we're actually looking at a view that is not vertical but about 20 degrees off or so, also more commonly known as a dorsoplantar view. Also the FC AP control gives us the same view, the same orientation, except in this case we're dealing just with black and white, no colorization, and also there is a transparency factor added. So again, we are simulating a dorsoplantar view. That again is the FC AP view. To return to our normal state, we go up to Views and Render Type, and our default viewing render type is CB Bone. Clicking on that, we get back to our original render type, which is CB Bone, and then AP Direction returns us to our original orientation. Let's take a closer look at some of the different render types, Views and Render Type. Again, the default is CB Bone. We also have several variations of bone where we have transparent or translucent skin overlaid on top of it. We also have a couple of other views simulating X-ray views, such as X-ray and MIP, and even a transparent colorized view where different types of colorization and lighting have been applied to the bones. Let's take a look at the bone and transparent skin render type. And we'll make a slight adjustment. We can see that the more dense cortical bone, such as we find on the shafts of the long bones, has the typical white appearance that we would expect. Some of the softer bone that we have at the end of the long bones has this yellowish appearance to it. And then the softest tissue is this translucent purple color, indicating the skin. So we have three different colors representing different degrees of density, and we also have some different variations on translucency or transparency to enable us to see through the softer tissue and view the more dense tissue. We can also get a better idea of how the different render types work if we go to 3D definitions. What we see here is a graph of the signal that produces the images that we see. The bottom axis is our density axis, starting at 0 on the HU scale, negative numbers and positive numbers. And then also we have translucent or transparent down at the bottom and more opaque as we go up the Y scale. So for the translucent skin rendering, we have this area that's mostly translucent on the lower end of the scale, which gives us the translucent skin. For the more dense and opaque bone, we have the second rendering group over here. Notice also that we have colors that coordinate with the different color tissue. Taking a closer look at some of the tools that are available to us under 3D definitions, we can, for example, see that this particular rendering is called Bone Transparent Skin. The background color is typically a neutral gray, but by clicking on this we can select any other color for the background color behind the rendering. Any changes we make, by the way, we can always reset them to the original default settings for that particular rendering. As we mentioned earlier, we have two different ranges set up here, one for the translucent skin and another for the more opaque bone. We can add additional ranges by checking boxes range 3 and range 4 and then customize them accordingly. The ranges themselves are identified by the area covered underneath the different points that make up the shape of the range. We can change some of the overall appearances of the 3D renderings as well by changing the ranges, and we do that by left clicking on a dot. We can grab the dot and move it, change its location, thus changing the shape of the range. This will include making something more or less transparent if we move the dots or series of dots up or down. And we can also click on each dot and change the color of what the rendering will look like by making each dot and therefore this segment of the range a different color. And we can also change how much density is covered within that range by grabbing and moving the dot to the left or right, thus including less dense tissue or more dense tissue. We can further customize the different ranges by changing some of the different characteristics of them by making adjustments to the points. For example, by clicking on this particular point on the upper end of the translucency scale, I now see that the HU value associated with that particular point is -99. The opacity level is 1 as opposed to some other point, say up here on the end of the bone, that has a much greater opacity factor as well as a much higher HU. The colors that are associated with it will indicate the colors that we see on the rendering, and those again can be changed by clicking on color and then selecting from the color palette. We can also affect how the light shows and affects the rendering by selecting light or unchecking the light box. The lock opacity for range moves should also remain checked by default, and what that does is when you adjust the ranges, which you can adjust by moving the sliding HU scale, notice how all of the ranges move in synchronization, and they're changing the overall density of what we're viewing in the 3D rendering window. Everything is moved in synchronization. You should keep the lock opacity for range moves box checked. If you want to create your own custom renderings, you can, for example, add additional ranges, change the background color, change the color of the different density tissues in the different ranges. You can then click Save As, and the default location where the rendering libraries are stored, you can type in a name such as Test 1 or Test 2 or whatever you'd like it to be. Save it, and then that rendering type will appear under Views, Render Type, and your custom rendering will appear. For example, we previously named this one Test 01 PA. Clicking on Segmentation, we see that we have a number of options available to us, including Freehand Erase, Remove Bone. Also, when we have segmented out a portion of bone, we can invert or show the part that we have taken away and not show the part that was remaining. We can also reset the segmentation, and we can also create and export an STL file. First, let's look at Freehand Erase. Clicking on Freehand Erase, I'm going to take my mouse, left click, hold the mouse button down, and as I drag, notice I'm drawing a line, which I can draw through any part of the 3D rendering. When I let go, I have segmented out or removed the area within the line that I drew. If I draw a second line, again left clicking, holding down the mouse button, and dragging, and letting go, I have segmented out a different area. Notice that part of my original area has been restored. If I want to remove and keep removing parts of the 3D rendering, I'm going to press and hold the Shift button down at the same time that I left click and drag. So I'm holding down the Shift button on the keyboard, left clicking and dragging, and now I'm going to continue to remove different parts of the anatomy. I'm going to uncheck this and rotate a bit so I can get a better view of what's left. And if I want to remove some more of the tibia in this case, again, Freehand Erase, I'm going to left click and drag a bit, still holding the shift button down. Let's get rid of this other tibia as well. Still holding the shift button down. I'm just going to uncheck so I can rotate without removing any additional bone. If I hit Invert Segmentation, what I cut away is now visible. If I hit Invert Segmentation again, it goes back to where it was before, showing the parts that were left after I cut away. I can also undo my last, and every time I click on that, or if I press Ctrl and Z at the same time, I will restore piece by piece the different segments that I had cut away. If I wanted to remove all of the segmentation and restore completely back to the original rendering, I can also click on Reset Segmentation and everything will be restored to the original rendering view. Now the other segmentation tool that I have available to me is Remove Bone. First thing that I would like to do is adjust my HU scale so that I have removed all traces of soft tissue, like you see here, so that the bones are completely isolated with no tendons, ligaments, or other soft tissue in between. Then I'm going to click on Remove Bone and then click, in this case, on the tibia. The tibia is now removed. If I want to click and remove an additional bone, I need to press and hold the Shift key down, and I can remove an additional bone as well. Sometimes, if the bones are spaced very close together, or if there's noise in between the bones, or additional soft tissue or soft bone, you may get more than one bone removed during this process. We can always undo the last and make an adjustment to the HU scale and then try clicking on it again. So after making a slight adjustment to my offset scale, I'm going to again press and hold the Shift button down. This will allow me to continue to remove segments. Clicking again on the tibia, and I'm also going to click on the fibula as well. Letting go of the Shift button, I'm going to uncheck Remove Bone, and now we'll be able to rotate around and get a really good look at the top of the talus on both of my feet. And again, hitting Reset Segmentation, I can restore the rendering to its original condition. So again, keep in mind, the more closely the bones are together, especially if they're touching, or if you happen to have a fairly noisy scan. 2 feet scans tend to have some more noise than 1 foot scan, or if you have presence of a lot of metal, it may be harder to segment out individual bones by using the Remove Bone. The Freehand Erase may give you better results. Wrapping this up, the Create STL file is not based on what you see in the rendering window, but rather strictly based on the number that you enter under STL HU threshold. What you need to do is enter a value that you think represents the density of the bone that you want to create a STL file of. For example, 2000 HU or 1000 HU. Create the STL file, save it, and then you would have to import it into a viewing software such as a CAD/CAM type of software or rapid prototype software that will enable you to create a solid object for 3D printing purposes from that STL file. CubeVue will not show you what the result looks like, so there's a bit of guessing involved. There will be additional improvements to this feature down the road, but for right now there's a little bit of guesswork involved. This video was created using CubeVue version 2.809. Some of these features are available in earlier versions of CubeVue as well. To upgrade to version 2.809 or whatever the current version is, please be sure to contact CurveBeam technical support to arrange an appointment for the upgrade.